In this video, we're going to take a look at the solutions to the quote-unquote cardboard Bellwork problems. So we have two problems here we're working with. One of them is one that should be pretty familiar to you, and that's number one here. So a square of side r inches is cut out of each corner of an 8-inch by 15-inch piece of cardboard, and the sides are folded up to make an open top box. We did a problem similar to this one the first few days of school, and this one just has some follow-up problems we want to take a look at as well. So you can see there's kind of a faded picture here, but I drew an 8 by 15 rectangle, and then I drew a square in each corner of the rectangle and labeled each side of the square R to show what I'm cutting out so I can fold this up. And when I do cut those squares out of each corner and I fold up each side, it creates a box like the one to the right here. And the dimensions of that box, since the original length of the cardboard was 15 and I'm taking an R off of each side, the length is 15 minus 2R. The width becomes 8 minus 2R for a similar reason. And when I fold it up, a common misconception is that the height of the box will be 2R, but remember when you fold it up, only 1R is actually folding up to create your height. So drawing a picture and labeling it is our first step of any problem solving process. So when we're doing any problem where we have the ability to draw a picture and label it, we should do so. Part A asks you to write a function representing the volume of the box as a function of R. Pretty easy to do once you have the picture here, as long as you know that the volume of a rectangular prism, also known as a box, is length times width times height. So the volume with respect to R, and you could have just wrote V equals, but you'll get used to seeing this notation, function notation. The volume with respect to R equals the length, 15 minus 2R, times the width, 8 minus 2R, times the height, which is R. No need to distribute any of that out, just said to write the function, didn't say it had to be in any particular form, so you're good to go with that answer right there. Part B says state the domain of the function in the context of the problem. Normally, when we are asked about domain, we're asked about the x values. Because R is in the place where x normally is, we're really asking ourselves, what are our possible R values? Many times when we're looking at domain, instead of asking ourselves what are the possible values of some variable, we should ask ourselves what values are not possible. So the one small value that's pretty obviously not possible is that R cannot equal 0. Because if R is equal to 0, then we don't even have the height to our box. In fact, not only can R not be 0, but it can't be negative. So we know that our radius has to be a positive number. How positive can it be? Here's where you have to analyze a little bit. You can do this by plugging in some values of R. So if you plug in 1, you'd have a 1 by 6 by 13 box. If we go up to 2, we'd have a 2 by 4 by 11 box. If we go up to 3, we'd have a 3 by 2 by 9 box. If we go up to 4, we'd have a 4 by 0. We have a problem. So we can't go any higher than 4 with our radius. No, I'm sorry, I shouldn't have said radius, our R value. I don't even know why I said radius. But we can't go beyond 4 because then we wouldn't have a width to our box. So the smallest value we can have has to be above 0. The greatest value we can have has to be below 4, which is why our domain is from 0 to 4, not including either of them, which is why I use parentheses there. So please remember this is interval notation. That parentheses and this parentheses don't mean this is a ordered pair. It means that your possible R values are between 0 and 4, not including 0 or 4. So you do have to analyze sometimes when you're asked about domain or range. Part C asks us to graph the function and find the largest possible volume. So to graph the function, you actually type this into your graphing calculator, and you do not have to distribute this out. You can just graph it as is. So I can go in and type y equals 15 minus, I do have to use x's, so can't change your variable on here. 15 minus 2x times 8 minus 2x times x. And remember, when you graph, you generally want to start in the standard window. And unfortunately, that doesn't really show me what I want to see here. So if I really want to look at this, I know that my domain can only go from 0 to 4. So I'm going to go to my window and I'm going to restrict this a little bit and make my minimum x value be 0 and my maximum 4. And then in terms of the y's are representing your volume. So you know you can't have a volume smaller than 0. And in terms of your large volume, you knew it had to be bigger than 10 because it was off the screen. So maybe I'll just do 100 and see what happens here. Oops. Let's go back and delete those and make our y max 100. If I'm going to go up to 100, I'm going to also change my y scale to go by tens just so it's easier to read my graph. Now when I hit graph here, let's see if I have enough, and we're good. So we can see everything we need to see here, and keep in mind that the x-axis represents R values and the y-axis represents V values or volume. So I drew a little sketch of this on my solutions, and you can see that my R-axis goes from 0 to 4, and remember R is in inches. And my y-axis, which is my v-axis, goes up to 100 there. I didn't make any interval markings, but it's in inches cubed. So there's my little sketch, and I had to graph the function and find the largest possible volume. Well, as long as you understand that this graph, each point represents an R value and its corresponding V value, the largest possible volume, V value, is going to be at the maximum at the highest point. So luckily for us on our calculator, we can find the exact highest point by hitting second, trace, and one of our calculate options is maximum. So we can choose option 4, and it's asking us for a left bound. Now you can either scroll over to the left of your maximum point, or even better yet, you can just pick a value that you know is over there. So if I pick R equals 1, or really X on the calculator, and hit enter, you'll see this little arrow here, which is going to be the left bound for where the highest point is. I need to choose something that's to the right of that. So it looks like I can choose 2 and I'm going to be okay. So I'm just going to hit, when it asks me for right bound, 2, enter, and then you'll see another arrow come in. So what your calculator is doing is bounding this area off, and it's saying it will find us the highest point there. So if we go to guess, the only reason it says guess is because it gives us an approximation, but it tells us the maximum is at about 1.6 repeating, it looks like, and then 90.74 for the y value. So that represents a point, and if we go back to the solutions, a point, this 1.6 repeating represents an R value, and 90.741 represents a V value. So when the R value is 1.6 repeating, the V value is 90.741, which is our maximum volume. So that takes us to part D. What should the area of each cutout square be in order to produce a box with the maximum volume? Well, if the maximum volume of 90.741 occurs when the R value is 1.6 repeating, as long as you remember that these squares are R by R, it's really easy to find the area of a square. You just take the value and multiply it by itself. So 1.6 repeating squared gives us approximately 2.7 repeating inches squared, and you could easily do that by typing it into your calculator. Moving on to number 2. This is a problem that students generally are not fans of. Probably the easiest way to put that. So we have a small satellite dish is packaged with a cardboard cylinder for protection and shipping. The parabolic dish is 24 inches in diameter, 6 inches deep. The diameter of the cylindrical cardboard box is 12 inches. How tall must the cylindrical box be to fit in the middle of the dish and be flush with the top of the dish? So it's a little bit hard to see some of my markings here, but I drew a parabola shape to represent the dish. And if you've ever seen a satellite dish, and they're hanging on people's houses for DirecTV and stuff, it does have that parabolic shape to it. In the middle, there's an antenna that receives a signal, which is how you get your TV. Your TV signal gets to your TV, I should say. Well, when it's packaged, you need to protect that little antenna there. So a cardboard box goes right inside of the dish, and that way, if something would fall on top, it wouldn't crush it. Needless to say, it gave us some dimensions, so we know that our dish is 24 inches in diameter. We know that it's 6 inches deep, and we know that the diameter of the cardboard box goes inside here is 12 inches and is going to be centered right in the middle. And our job is to find how tall that box needs to be in order to fit inside the dish. So most students don't do what I did here on the answer key. They draw a picture and then they're kind of at a loss. So one problem-solving strategy that you're going to, want to take advantage of from time to time is to take your picture and just put it on a coordinate plane, preferably some kind of coordinate plane where you can put the origin as a key spot. So I put the origin at the bottom of the antenna here, and then that allowed me to say if this is the point 0, 0, and I know that the diameter of the whole dish is 24, then this far right side here, I have to go over 12 and up 6, so it gave me a point. And I did the same thing on the left-hand side to get the point -12, 6. Once I have those points, I can get an equation for that parabola. How? Use your calculator. So I went into my calculator, stat, edit, and I preloaded those points, 0, 0, 12, 6, and -12, 6. I already know the shape of this is a parabola, so to get my equation, I can simply go to stat, edit, how about stat, calc, quadratic regression, list 1, list 2, frequency list, and I want to store this thing. Before I do that, I believe I reset my calculator. So in the last video, you saw that you can turn on your stat diagnostics, and when you turn that on, it'll tell us how good of a fit this is. So I'm going to go back and hit stat, calc, quadratic regression, because we know it's parabola. List 1 is our x's, list 2 is our y's. We don't mess with the frequency list. I already have an equation stored in y1 from the first problem in this set, so I'm going to alpha f4, store this one in y2. And when I don't go down to calculate, here's the equation of that parabola, y equals 0.042 approximately, x squared. There is no b value and no c value, so that's my equation, y equals 0.042 x squared. You can see right here that my correlation coefficient is 1, which means this is a perfect fit. When I go to my y equals, I need to turn my plot on so that the points show up. So normally we go to stat plot and turn it on, but you can just turn the plot one on as long as your list 1, list 2, and everything are correct. And I'm going to turn off the first equation because that was from the first problem. And then remember, when you're doing a statistics problem, you want to choose the zoom stat option for your window. And there's our points, and here's our parabola. So the question is asking us how tall does the box need to be? And as long as we know that this is a 12-inch diameter, then I need to go halfway to get to one of the heights of the box. So all I really need to know is what is the height of my parabola right here, because once I have that, I can just subtract it from the height up here of 6. So there's a bunch of ways you can do it. One way is to just hit second, trace, value. And when I do that, I want to know what is the height of the parabola when x is 6. Tells me the height is 1.5. So this distance right here is 1.5. All the way up to here is 6, which means if I want to know what the height of that cardboard box is, all I have to do is subtract that 1.5 from the 6 to get 4.5 inches. In class, I'll show you some other ways that you can find values on a graph like that. But for now, we'll leave it there and pick up in class.